Hello, Tanya Laird here, and welcome to Part 2 of Lecture 7 of ENGR 231 Engineering Statics. In this part of the lecture, I would like to just really dig into the rigid body assumption and discuss why it's important and some of the implications of it. And the reason I'm looking at this in this particular lecture is that to really explain the rigid body assumption, I really have to look at it in terms of moments. But I guess we could also look at it in terms of, say, application of forces and displacement of forces and things like that. But in terms of what we know from statics, or in terms of the course content of statics, it really becomes apparent why the rigid body assumption is important when we start exploring the topic of moments. So, rigid body assumption, why do we do it? Or why do we use it? So, two of the main equations, or two of the main assumptions that we use in this course, or two of the main models, I should probably say, that we use in this course are the point particle model and of course the rigid body assumption, or the rigid body model. Now, it's pretty easy to see why we use the point particle model in terms of the previous discussions we've had. Using a point particle model allows you to completely ignore moments and rotation in terms of equilibrium. But why do we use rigid body? Why not just, why do we use that? Well, first of all, let's do a bit of a review. What is a rigid body? Now, if you're having trouble remembering what it is, again, a rigid body is one that does not deform. A rigid body does not deform under load. So in other words, if we have an object of some particular shape, if we apply a force to it, it doesn't stretch out. Most objects, well, actually all objects, all real objects, if you apply a force to them, they're going to deform in some manner. Now, that deformation can be very small. I think in previous lectures I've discussed the example of, say, I'm walking across a incredibly strong, very thick concrete floor slab or something like that, and my weight versus a very strong concrete floor is negligible. That floor can withstand an immense amount of load. If I'm walking across that, I'm not even putting a fraction of 1% of what that floor is designed to withstand. But even then, even if I had some ridiculously strong, even if I made a ridiculously strong floor out of 2-foot thick solid titanium or something insane like that, even then, the deformation would not be zero. Or even if I had some incredibly thick, strong beam or deep beam or something like that. Imagine I had a 10-foot deep titanium beam, and all I put upon it is the weight of a feather. So you have this incredibly strong object, and you're applying an incredibly small load to it. The deformation that it would experience would still not be zero. It would still experience some deformation. So it doesn't matter how strong your object is, and it doesn't matter how low the force you're applying to it is, even the slightest of force applied to the strongest of object still produces some non-zero change in shape. So this is not the case in real objects. But I've never actually really discussed why that is important. So we discussed previously what the rigid body assumption is, but I've never actually really discussed why that is important for engineering statics. So, why is the rigid body assumption important? So, as we'll see in later examples, we are going to explore how forces distribute in objects of size. So let's for a moment say I have an object, and we haven't talked about this too much. You know what, actually, let me just do a very simple object. I'll keep things relatively simple right now. Let's say I have a beam. And let's say I apply a force to this. This beam is just sort of jutting out of this wall here. Later we'll learn this is called a fixed support, but you don't have to worry about that right now. So let's say I have a force applied to this, a force F. Now, in terms of what we've seen so far, we know that this force, if this beam has a certain length, has some length to it. At this location here, this beam is going to experience this at this look. So let's say this again. Let's just say this force is applied at the end of the beam. I'm gonna go ahead and give this dimension to make this a little more explicit or specific. So you have a certain beam length L. Let's talk about this point here. Let's call this point O, the origin. The moment about O. Well, that's fairly straightforward. Actually, I'll be able to do this in black. The summation of moments about O is simply equal to L times F. Again, the moment this force is going to produce about the origin, or the left-hand side of the beam, is just the force times the length of the beam. That's just the length of the moment arm. Everything is nice and perpendicular here, so we don't have to worry about angles and thetas and cross products and all that kind of stuff. It's just L times F. No big mystery here. But notice what I assumed here. Or maybe you didn't notice what I assumed here, or maybe you haven't quite seen this yet. I have assumed that this beam is a rigid body. I have assumed that this beam actually hasn't changed shape. So, what would happen if the beam actually did change shape? So again, a force is applied to this, and then I said, okay, what kind of moment is present at the left-hand side of this beam? And that's fairly straightforward. That's just L times F. We have a force times the length, L times F. Pretty simple. Grade school simple. Well, maybe high school simple, depending on how you define grade school. Rigid body assumption. But what if this is not true? What if beam can deform? What happens then? So let's say we have the same point O here, and I now have the same beam. Now, initially, we'll say this thing is at length. It has a length of L. And I'm going to apply the same force F to this beam. And some length L here. Some length L here. So how does this, what if the beam can actually deform? What if it can actually bend? What if it can actually twist? What if it can actually expand and shrink and et cetera, et cetera? Well, logically, what's going to happen? Well, assuming it's fixed on this end, what is going to happen to this beam? It's going to do something like this. Here. Now this is, well, maybe I don't want to show quite that much deformation. That's exaggerated a bit. Let's show something more like this. And even this is greatly exaggerated. It's going to do something kind of like this. We're going to end up with a force or a beam that's deformed more like what we have in the orange here. So this beam, as it bends, it's not, obviously it's going to move upward. That's fairly straightforward. But if you've ever actually dealt with something that's bending, you would realize, or you could tell me, that this thing's not only going to bend upward, but it's also going to move to the left. The upper end of this beam is going to bend to the left. So it's going to go from this shape to something more like this shape. It's going to bend both up, but also to the left. And so, the beam tries to conserve its length as much as possible, and so if it's going to bend upward, which it has to because of this large upward force, or even a non-zero force is large in this context, because we're not ignoring deformations, it's also going to bend to the left. But why is that important? And the reason that's important is as follows. Because if you look at this, what happens to the moment arm of the beam, or of that force? It decreases. So maybe this is an L1. All right, I'll just call that, I'll leave that as L. Maybe I'll call that LD for L deformed. LD for like an L deformed. And L deformed is less than L. And so what's going to happen is the moment arm of that beam is going to change, which means the moment, so the moment arm is different. The moment arm is different. And the importance of this is that usually when you try to predict how far something is bending, you use the moment on the left end of that beam. And so, or if you look at the stress in that, you're using the moment on the left end, on that left end of the beam. And so, again, often in beam design, oh, let's go ahead and keep that. Sorry about that. Often in beam design, we consider the maximum moment, or we design to the maximum moment. But however, as we see here, the forces applied will actually change the geometry. The forces applied change the geometry, and thus the actual moment that is present. And thus the actual moment present. And thus the actual moment present. So again, if you are trying to find the maximum, if you're designing your beam according to the maximum moment, which we frequently do, if you're applying a force to it, well, the geometry is actually changing, and the moment arm changes, which means you're changing the maximum moment arm. So the force changes the geometry, but in turn that geometry changes the moment, which affects everything. And so, again, this is the fundamental reason why we often make the rigid body assumption. So, now, I have drawn this as truly an exaggerated form. Truth be told, it doesn't deform anywhere near this much. If you were to take a concrete beam or a steel beam and try to bend it this much, it would snap in two long before you ever got anywhere near this actual level deformation. So, truth be told, the actual or the real deformations experienced by steel beams or experienced by beams and columns, etc., or let me just say experienced by most civil and mechanical engineering systems. I'll keep it nice and generic. Civil and mechanical engineering systems, or examples, or applications. I should probably say applications. Are far below where change in moment arms become important. And what I mean by change in moment arms, I mean change in moment arms produced by the actual loads applied. Therefore, in most cases they are neglected. they can be neglected. So we are going to do, as we go through this lecture, we are going to deal with many cases where we assume something that will not deform, and we'll calculate, okay, well, if that thing doesn't deform, what are the, how do forces distribute through that body? But, and again, realizing that truth be told, the actual or the real distribution of forces in that body are going to be slightly different than what we get from assuming that the object doesn't deform at all. But in reality, those would actually be fairly close together. They would be within a few fraction of a percent. So the question then is, they might ask is, well, why don't we just do with the whole thing? Why don't we actually consider the full non-rigid body? Why not just consider deformation? So here, I said that as this thing bends, the length, the moment arm length changes and that kind of thing. But if you actually start looking at complex systems, there are many different things you have to consider. So, first of all, a few of the big things, you'd have to consider the material. And these things include both the modulus elasticity, and the yield strength, and maybe even the ultimate strength. And you'd have to consider some things that we call cross-sectional properties. Cross-sectional properties. And these include things like cross-sectional area and moment of inertia. Now, you wouldn't need to use this one in particular when you're doing bending design, but you often need to when you're dealing with other things. And polar moment of inertia if you're dealing with, say, torsion or something. But as far as what these are, well, actually we'll deal with this one here, moment of inertia, later in the semester, and area isn't too difficult. But all of this and how these interact is fairly complex, and really all this stuff is an entire course unto itself, and this is mechanics of materials, and actually some higher level courses as well, if we're dealing with nonlinear effects, second order effects, and a whole bunch of other things. So, suffice to say, I don't want to spend too much time on this, but the basic idea is that if you actually want to model how far this actually deforms over, you want to predict that, you have to use a whole bunch of equations and a whole bunch of knowledge describing both the material that object is made of, and a lot of stuff describing, okay, what is the cross-section of that particular member. And that takes a lot of, again, to teach you that properly is a bit beyond the scope of this course, and it's not, at a basic level, mechanics of materials is not too bad, and you'll actually take, if you're civil and mechanical engineering students, you'll take that after this course, but it is an entire other course unto itself, and so it's almost an entire, well, it is an entire semester beyond this. So by doing this one little assumption, just assuming things don't bend at all, or deform at all, we're allowed to avoid or allowed to ignore both the material properties and the cross-sectional properties, which would otherwise be quite difficult. But I did want to, again, that's kind of a continuation of what we've seen earlier in the semester, earlier in the course, but I did want to sort of give an explanation of why it is that why it is important that we use the rigid body assumption. And this is not the only example of why you might use this. There are a whole host of other reasons I could think of, including things like axial deformation, and also torsion or twisting of a member. But this is perhaps the simplest to describe, where if you're dealing with a moment and trying to calculate the moment arm, well, if you don't know if you don't know the material properties, you can't predict how far that thing bends, and if you don't know how far the thing bends, you can't actually predict the moment arm, and thus the maximum moment at that point. Anyway, I know this is a bit theoretical. I know this may be a bit dry or something like that if you're just looking to get through the more mechanics of the course or the more mathematical aspects of this course. But for those of you who are interested in the more theoretical aspects of statics, I hope this video proved a bit illuminating, at least at a basic level. All right, that'll do it for now. Let me know if you have any questions. If not, I will see you all later for part 3 of this lecture. And as always, thank you.